This is lecture 5. I do recommend you going back and listening to prior years because I do explain it different every year. People ask different questions. You might get different input. So yeah, definitely, and especially in forensics and stuff like that. Obviously I explain it different every time. Okay, what if I was to give you a number, 113, and 5, 7, 15, 32, and 69? Could you figure out the combination of those numbers that equals 113? Yeah, you could. Okay. We're going to get back to that. Okay. So, let's talk about some different classes of problems. You will see multiple questions on this on multiple exams. Okay. First type of problem is a class P problem. It's a set of problem whose solution runs in time bounded by polynomial functions of the size of the problem. I'll get there. Set of problems that are easy to solve can be solved in polynomial time, which is an amount of time that's roughly proportional to the size of the problem. So if I told you to multiply 5 times 4 together, how difficult is that? It's very simple. It's a very small problem, very simple, but if I told you to multiply more numbers, it would get more complex. So the larger the problem, the longer it will take. How about if I told you to search for a book from the box of books? Could you do that? What if I told you to search for a book in the Library of Congress?
Easy.
Without a card catalog.
But see, there's the difference though. The box could take longer than the Library of Congress.
It could.
Just because they sort them.
Because they're sorted. But you can see, so searching for a box of books could be easy, or it might take your entire life, depending on the size of the box and what you're looking for. Okay? So that's what a class B problem is. Everybody got that? It's a problem bounded by polynomial time of the size of the problem. Class NP, non-deterministic polynomial. A set of problems whose solutions run in time bounded by polynomial functions of the size of the problem, just like a P, but assuming the ability to guess perfectly. Okay? So what if I could go into the Library of Congress and guess exactly where the book is and go grab it? That's an NP problem. Okay? Said standards for non-deterministic polynomial time, where non-deterministic is just a fancy way of talking about guessing a solution. Okay? I tried to add more verbiage to explain it in here. A problem is an NP if you can quickly, in polynomial time, test whether a solution is correct. So I can walk right into the Library of Congress, walk to that specific shelf, and see if that's my book or not. Easy enough? Okay? So I can test whether my solution is correct or not, without worrying how hard it might be to find it. Okay, they're still relatively easy. If only we could guess the right solution, we could then quickly test it. Okay? So, I have 5 times 4. I'm going to guess 20, and I can very easily verify that 5 times 4 is 20. Okay? A problem is NP complete if it can be verified. So I can guess where that book is, but now I'm actually going to go and grab the book and verify that it's there, and some sort of quick algorithm. Maybe an algorithm is use the card catalog. Okay? So if the answers can be verified quickly, and a quick algorithm to solve the problem can be used to solve all other problems quickly. In other words, I can verify it and come up with a way of doing it. Okay? That's what the big difference is. So NP complete, I can assume that I can guess perfectly, in other words, get the right answer, and I can test it, and I can make a plan or an algorithm to do this over and over and over. That's NP. You really need to know these 3. They're on multiple tests. Okay, EXP, set of problems whose solutions run in time bounded by exponential functions. Do we all know what exponential is? So 2 times 3 is 6. 2 to the 3rd is 8. Okay, 2 times 2 times 2. See, there's, a big, I'm assuming everybody knows that. Okay. So they're bounded by exponential functions of the size of the problem. So using exponential numbers makes things much more difficult. Easy enough to remember, EXP exponential. Easy enough. Okay. Fundamental result, it says polynomial functions might be a subset of NP, which might be a subset of EXP, but we're not positively sure at all times. It's not always that. This is not always true. It says NP complete problems do not guarantee that there is no solution easier than EXP. So an NP complete problem might become exponential. And every NP complete problem has a solution that runs in time proportional to 2 to the n, where n is small. In other words, it could still take time. Okay, they can be modeled by threads. And if you know, anyone know what threads are? I'm going to give you a prime example of what threads are. I wrote a program when I was at University of Tulsa, a network sniffer. I had to read in network traffic and analyze it. It was awesome. Program read in the traffic, analyzed it, and output the results. Anyone see a problem with that? So I read in my traffic, I went through that traffic and analyzed it, and then I output the results. What do you think was happening while I was analyzing and outputting? Other traffic was zooming on by. There's a problem with that. So I had to rewrite my program in threads. So I had one thread that all it did was kept grabbing all the network traffic. That's all it did. Then one thread that basically said, hey, as long as I have traffic saved over here, let's analyze it. He just kept analyzing as long as there's traffic. Then the third thread basically said, as long as there's stuff that's been analyzed, let's output the results. Worked much better that way. I didn't lose any data that way. So it can be modeled by threads. Interceptors may use other information to simplify it. So basically, interceptors will use anything. Now let's talk about hard problems. Some problems are hard to solve. Do you agree with that? Yeah, there's always stuff that's hard to do. Okay? There could be no algorithm is known, or an NP hard problem such as machine scheduling or bin packing. You all know what a bin is? It was basically, you ever seen that? You got to figure out which combination of stuff fit in the bin, that kind of stuff. And we're going to go over the knapsack, which we're going to see in a minute. Is it good or bad to have hard problems? I think it's very good. We want hard problems. Right, we want that. We want to keep our stuff secure. Okay, so data encryption relies on difficult to solve problems. Now let's talk about secure encryption systems. This is modern techniques are based on hard problems. NP complete, in other words, we can get the answer, can test the answer, and we can write an algorithm to do it. Can you imagine if we didn't have the ability to get the answer? That would suck. Or we didn't have the ability to test the answer? That would suck twice. Or what if we didn't have an algorithm for it? Then what good would it be? Then it would be, oh, I'm just going to randomly throw a bunch of letters and there's your encryption. I mean, that would be terrible. Okay. Okay. It says involve heuristic searching. In other words, it says usually works, but not always. In other words, it could be very difficult to do. That's what you want. You want stuff that's going to take a very long time. Maybe it's not hard to do. It's kind of like that whole brute force thing. Would it be hard for you guys to come up here and type in different passwords? No. No, it wouldn't. Okay. But you would hope that it would take long enough before you got to the correct one. Okay. All right. Now let's talk about some public key. First of all, is public key symmetric or asymmetric? What is it? Public key. Okay, first of all, which one's which? What is symmetric and asymmetric? Which one is the same key? Symmetric, same key. Public key is the different key. That's right. I can put my key out on the public, so I can encrypt it with my public key, and you guys can decrypt, or I can, whatever. You encrypt it with my public, I can decrypt with my private. So that's asymmetric. Okay. So, Diffie-Hellman, public. Merkle-Hellman knapsacks, public. RSA, public. El-Gamal, hashing algorithms. All these are public. Okay. Secure encryption system. Let's talk about this now. Something called satisfiability. So if I told you to pick V1, 2, and 3 such that V1 and V2 or V3 and not V2 or not V3 is true. So what is the answer? What is V1? Okay, first of all, do y'all know what Boolean algebra is? You know what an and means? If I have 1 and 1, what's the answer? 1. It's true. True and true, the answer is true. If I have true and false, the answer is false. Because with an and, both sides have to be true. Now an or, what if I say true or true? True. True or false? True, false, or true? True, false, or false? False. Okay? Not negates that. So for this to work, what does V1 have to be? Since it's got an and next to it. For this whole thing to become true, so we know with an and, both sides must be true. So since I have V1 and something else, what does V1 have to be? V1 has to be true. Everybody see that? V1 has to be true. So we're going to get my little pencil out here. He's going to be, we'll just put a 1. What? Well, forget it. It's true. I'm not going to write it. It'll take me too long. So V1 is true. Everybody agree with that? Everybody see how we got that? Since it has an and, we know for the entire thing to be true, at least both sides of the and have to be true. So since V1's on the left side of the and, V1 has to be true. Okay. So let's start with the right side. So if V1 is true, go all the way to the right. So then what is not V1? Okay, what is this guy right? Where's my marker? What's this guy? So remember, V1 was true.
V2 would have to be false.
So not V1. So this right here becomes what? False. So it's not true. So this is false. And since this is on the side of an and, this entire side must become true. Since we know this is false, this has to become true. So, if this has to be true, then what is not V3? So what's V3?
False.
V3 is false because not V3 or not false becomes true. So now we know V1 is true, V3 is false. Everybody with me? So over here. So if V3 is false, then what does V2 have to be?
True.
True. So we got true, true, and false. Everybody see that? Hopefully. Brett? You got it?
Yeah.
Okay. So what if I told you to pick a knapsack, V1, 2, and 3, from the subset of 0 and 1, and either V1 can be a 0 or 1, V2 can be 0, 1, V3 can be 0, 1. So pick that value for each of them, such that V1 times A1. So what is a number times 1?
1. Or that number.
The number. So if A1 is a 3, so if V1's a 1, what's the answer of 1 times 3? 3. What if V1's a 0? So 0 times 3 becomes 0. So knapsack is pick a combination of V's to go with your A's that equal the target sum. In other words, let me backtrack here for 12 slides. So what combination of 1 or 0 goes with each one of these letters to make it equal 113? So is it A times 0 or A times 1? First of all, what is the answer? Well, no. So that's 60, 70, 80, 90, 101, 18. So it's all but the 32. Everybody see that? Is that right? No, all but the 15. All but the 15. So 69 and 32 is 90, that's 101.
All but 15.
Yeah, 101 plus 7 is 108, plus 5 is 113. So, 5 times what? 0 or 1?
1.
Okay, 7 times what?
1.
1. 15 times
0.
0. 32 times 1. 69 times 1. So our answer is 1, 1, 0, 1, 1. Everybody see that? Everybody see that now? You have a question? Okay. So we wanted to know what combination of those numbers equals 113. Okay? Now remember, we were choosing the V's. The V's are either a 0 or a 1. So we know we need the 5, 7, 32, and 69. So we need the 1 times 5 plus 1 times 7 plus 0 times 15, because we don't want the 15. Then we add them all up and get 113. Okay, so we're going to go more back into that in a second. So this is a review slide. Remember, secret or symmetric key was n times n minus 1 divided by 2. Nothing new there. The public key was just 2n. Nothing new there. Okay. All right, public key algorithms. Let's talk about how those work. If we encrypt with the private key, we can decrypt with the public key. If we encrypt with the public key, we can decrypt with the private key. They're a key pair. They work together. You encrypt with one, you can decrypt with the other. Doesn't matter. So down here at the bottom. So take our basically we take our text, our plain text, encrypt it with a private key. Okay. Then we can decrypt it over here with a public key and get the value back. Okay. So an easy way to think about it. I think last week, didn't I show you guys my public key online? I think I did. So if you guys were to download my public key off the internet and encrypt something with that public key and send it to me, I'm the only person in the world that could open it. Okay? So that way we know it's going to Ken Dewey. Now if I encrypt something with my private key and send it out to you guys, who can open it? Everyone. Then what the heck good is that? They know it came from me. Because I was the only one who has the private key. I'm the only one who could have possibly created that. So that's why we can encrypt and sign things. Okay? Oh yeah, yeah, exactly. That's assuming the keys haven't been compromised and we didn't leave the computer online. Okay, so let's talk about Merkle-Hellman. 1978. These dates might become important in some time in the near future. Okay, it encodes a binary message. That is very critical. Remember, we're talking ones and zeros here. What combinations of ones and zeros got that to work? Remember we just did that 2 seconds ago? It was 11011. That was our binary message. So encoded binary message is a solution to the knapsack problem. It's an NP-complete problem because we can guess an answer. We guessed 11011. We can test it. And that's an algorithm and knows that it works every time. Okay? There's something called a simple knapsack. We're going to see what that looks like. We're going to use that. We're going to create a hard knapsack, which is exponential time. In other words, we're going to use some math in it. This is also one-way encryption. Okay? Now, I'm going to take this marker right here, and I'm going to change this to red, and this could be a pen. I'm going to highlight this word right there. Then I'm going to take this pen over here, and I'm going to change him to black and highlight it again. I'm going to take this pen over here. Now we're going to change it to blue. Highlight it again. Then we're going to, do I keep going?
Yeah, purple. One purple.
One purple. Okay, let's do it. I lost my marker. We need a purple. We need a purple. Highlight it again. So, when one of you says, well, I kind of don't remember that. So, exactly. One-way encryption. All right. Don't miss that one. Everybody's like so many times. So I didn't know you said that. Trust me, it's in the slides. Go look at slide 12. It's there. Okay. So let's talk about the general knapsack. So given a simple knapsack, in other words, A through N, 1 through N, that means however long it is, N means you keep going as long as you want, and a target sum, that would be that 113. So in other words, that's the 5, the 7, the 13, the 32, the 69. That's the simple knapsack. And the target sum of 113. Find the number of V's from the subset of 0 and 1 so that A1 times V1 plus A2 times V2, so on and so forth, equals T. Easy enough? That's what we did. So the simple knapsack is 9, 5, 2, and 13. Our target sum is 24. Then V becomes 1011. So in other words, 9 times 1 plus 5 times 0 plus 2 times 1 plus 13 times 1. So 9 times 1 is 9. 5 times 0 is 0. So we got 9 so far. 2 times 1 is 2. So 9 plus 2 is 11. 13 times 1 is 13. So 11 plus 13 is 24. Easy enough? Simple to do. So this is NP complete as long as we can guess V, which in this case was quite easy to do. Small enough, but we can make it more difficult as well. So far so good? Everyone with me? All right. Now let's talk about the super increasing knapsack. Okay, our simple knapsack must be super increasing. And there's the math for it. In English, a simple knapsack is super increasing as long as every number is larger than the sum of all prior numbers. So the 2 is bigger than the 1. The 5 is bigger than the 2 plus the 1. The 13 is bigger than the 5 plus the 2 plus the 1. Everybody see that? That's called a simple super increasing knapsack. Okay. What do you think happens if this is not super increasing? There might be multiple answers. And it does happen. So if I give you a question on a test, can you figure out which one's super increasing? You should be able to do that. Just remember, every number is larger than the sum of all prior numbers. So the 2 is bigger than all the numbers before it, which just happens to be a 1. The 5 is bigger than all the numbers before, which is the 2 and 1, which is actually a 3. The 13 is bigger than the 5 plus 2 plus 1. No problem? Everybody got that? Easy stuff. It's just like 27 steps to this, that's all. But they're easy. Yeah, you remember that whole NP thing? They're not difficult. There's just lots of them. Okay, so that's the knapsack. Okay, we're going to continue on. We're making great progress.